Muqcs is a JavaScript library for simulating quantum circuits, but there are already other software for simulating quantum circuits. So why would anyone want to use Muqcs?
Other software packages for simulating circuits are made of tens or even hundreds of thousands of lines of code. But Muqcs is under 3,000 lines of code, so it's a lot easier to study and understand for someone who wants to write their own simulator or who wants to reuse parts of the source code in Muqcs. If someone wanted to port Muqcs to another language, that would be pretty easy. All of the source code is contained in a single HTML file, which might sound unusual, but it sure does make it easy to search for things and to find comments and documentation on the different algorithms within Muqcs. If you're interested in mastering certain concepts within quantum computing, a great way to do this is to write your own simulator, in which case Muqcs could be a reference implementation that you can learn from and use parts of and modify as you like. Muqcs can compute several quantities related to quantum computing and quantum circuits. So it can perform arbitrary partial traces on any subset of qubits that you like to compute a reduced density matrix for that subset. And then that can be used to compute, for example, the phase of a qubit or the probability that measuring it will yield a 1. You might be familiar with other software packages like IBM's Quantum Composer, where you can drag and drop gates onto a circuit, and then there are these little widgets that show us the probability of measuring a 1, the phase of the qubit, and the purity of the reduced state for that 1 qubit. So these quantities are all easy to compute with Muqcs. Another example we find it in Quark, where we can see the probability of measuring a 1 for any qubit, and we also see a little block sphere visualization for each qubit. So Muqcs also allows us to easily compute the coordinates within the block sphere of any qubit we like. In addition, Muqcs can compute the entropy associated with a single qubit. It can also compute quantities associated with pairs of qubits. So, for example, the correlation or the concurrence of 2 qubits. There's also a subroutine within Muqcs to compute the magic of a subset of qubits as quantified by the stabilizer Renyi entropy. Because it's written in JavaScript, it runs inside a web browser, and there's no need for the user to install any additional software. Muqcs itself has no graphical front end, but you could build one that would run inside a web page. For example, if you wanted to make your own drag and drop interface for building a circuit, you could use Muqcs as the library that simulates the circuit, or maybe you'd like to make a web page with an interactive block sphere as a learning tool. Muqcs could also be used to implement part of that. On my own laptop, I can run circuits on 20 qubits, and it takes less than 100 milliseconds per gate to simulate a circuit like that, because Muqcs does have certain optimizations to achieve a reasonable runtime. There's also some subroutines in Muqcs to do pretty printing of matrices, which I'll show examples of. Muqcs is available on GitHub, and we can scroll down and look at the README file. If we right-click on this title and open up a tab for that, we find this web page, which contains all of the Muqcs JavaScript code in the page, so it's now loaded into the browser. And we could open up, under Developer Tools, we can open up a console with Control mouse wheel. We can make that as big as we like, and then we can go back to the README file on GitHub and look at some example pieces of code. For example, there's this circuit that we can simulate using this chunk of code, so we can copy that and then paste that into the console and hit enter. Now the circuit's been simulated, and this command at the end of the block of code prints out some of the matrices involved in the calculation. So this is what I referred to a moment ago as pretty printing. This column vector is the input state into the circuit. These are 2 of the matrices that represent 2 layers within the circuit. So in particular, the last layer here and the second last layer here correspond to this matrix and this matrix respectively. The other matrices in this case were omitted because we've got these ellipsis strings here. And this column vector is the output of the circuit, and it's been preceded by little strings that remind us which base states are associated with each of the amplitudes. So these got added because of this optional parameter that was passed in to this method toString. Now, if we would like to see more detail, we could copy this last command and then modify it a bit to print out the contents of all of the matrices representing all the layers of the circuit. So I'll just uncomment the appropriate code and rerun that, and then I'll make the text a bit smaller so we can see everything. So there's the input vector. It gets multiplied by this matrix for the first layer, then that one for the second layer, and so on, and that yields the final output. You notice in some of the matrices there are underscores. Those represent zeros. So sometimes the code will replace zeros with underscores just to make the matrix more readable. And this multiplication of a column vector by several matrices is performed on one line of code. It's this line of code here. So C matrix is a class for complex matrices, which are matrices that contain complex numbers. There's a method defined in this class called mult, which can multiply two matrices. But if we want to multiply several matrices, we can use n-ary mult, and we pass in a list of matrices. And matrix multiplication is not commutative, but it is associative. So what n-ary mult will do is it will choose an associative ordering with which to multiply these matrices to be more efficient. So it'll start by multiplying smaller matrices together. In particular, in this case, because this is a column vector, it's smaller than the other matrices. So the first thing that this method will do is multiply these two together, and that will yield another column matrix. That column matrix then gets multiplied by this matrix, and so on. So n-ary mult in this case will end up multiplying right to left, and that ends up being a lot more efficient than multiplying left to right. But the result is still the same. It turns out that for this circuit, there's another way that we can simulate it and get the same output, and that second way avoids computing any explicit matrices. So it's illustrated in this chunk of code, which we can copy and paste into the console. So now we have this pretty printout of what happened. This is the input vector, and layer by layer we see how that state vector evolves until we get the final output vector. So not a single 8x8 matrix had to be computed to simulate this. Instead, we made use of an algorithm called qubit-wise multiplication. Qubit-wise multiplication allows us to pass in any 2x2 matrix representing a single quantum logic gate or a unitary gate. We can say on what wire we want that gate to act. So the wires in the circuit are numbered from top to bottom, 0, 1, 2 in this case. We also specify how many wires there are in total in the circuit, or in other words, how many qubits there are. We give it the input state vector, which is going to be updated or transformed by this method. And then there's an optional parameter at the end, which is a list of control bits. So in this circuit, for example, this X gate has a control bit there, this X gate has a control bit there. More generally, we could have gates that have an arbitrary number of control bits or anti-control bits, and those can be passed in via this list. Now, if we'd like an explanation of how this list is interpreted, or an explanation of any of these parameters, what we can do is look up the documentation of this method in the source code. So I'll just copy the name of that method, and over here I'll right-click on the web page to open up the source of the web page, which contains all of the source code for Muqcs, and I'll search for the name of that method. So here's the definition of the method, and right before it there's a long comment that explains how it works, and there's also comments explaining each of the parameters on the method. So again, this file contains all of the source code. There's well under 3,000 lines of code here, and just to give an idea of the overall structure of it, we can search for the string class. There's a few utility classes. There's a class that defines complex numbers with some typical methods for operating on those. There's the class called C matrix, which I mentioned already. So this is for storing complex matrices and performing operations on those. And there's another class called sim, which is for more general simulation routines.